Alright, for this unit, for this review project, I'm going to be reviewing Unit 6, Projectile Motion. Pretty easy. Okay, so the important equations we used in this unit. This unit dealt with a fairly simple, and at this point in our class we should understand these ideas of acceleration, velocity, distance, velocity and acceleration vectors in a simple motion. Which is parabolic motion. So for these reasons we will only be dealing with the four equations we know well. The Suvat equations, so those are the equations over there on the right side of the screen. V is equal to u plus at, s is equal to ut plus 1/2 at. We can kind of disregard the third one in this photo, we don't really need it. And v squared is equal to u squared plus 2as, and then s is equal to uv over 2 times t. And remember, just a quick review here, s is equal to distance or displacement, u is equal to the initial velocity, v is equal to the final velocity, a is equal to the acceleration, and t is equal to time. So it's pretty easy there. We've used these equations a lot. Okay, so the first big idea in this unit, acceleration and projectile motion. So the first big concept we had to wrap our heads around was the idea of a zero acceleration in the horizontal direction and the acceleration of free fall, 9.8 meters per second squared, in the vertical direction. We did this in class through a simple experiment of dropping a ball and projecting a ball at the same time from the same height off the desk. When we did this, we discovered that acceleration only affects an object's vertical motion. There's only acceleration in the vertical direction. Both the dropped ball and the projected ball reach the ground at the same time. As long as the two objects are projected at the same height, the different horizontal difference, their horizontal displacements, has no effect on the time it takes for them to reach the ground. So there's the more interesting version of if you fire a bullet at the same height as you drop a bouncy ball or just a ball, the objects will both touch the ground at the same time in a perfect world with no air resistance, that is, which is basically this entire unit we discounted resistance, air resistance. Okay, second big idea, describe projectile motion. So the path of any projectile is known as its trajectory. The projectile is a trajectory shaped like a parabola, so it's called a parabolic trajectory. And then here I'm going to look at some position versus time graphs from our packet from this unit for the horizontal motion and the vertical motion of a projected object. So I'll cut to that. Okay, so when we're looking to describe parabolic motion, we probably want to know the position versus time graphs for the horizontal motion and the vertical motion of a projected object. So on the left here we have the graph for the horizontal motion. Disregard this scribbled out line, but if we start at a displacement of 0 horizontally and project a ball over time, the ball will increase its displacement constantly because it has a 0 acceleration in the horizontal direction, so we know its velocity remains constant and it'll come and hit the ground at a point. So that's the horizontal motion on a position versus time graph, and it's a linear relationship, y is equal to mx plus b. So on the right here we have the vertical motion for parabolic motion, and the object starts out at a vertical displacement, position of 0, if you're throwing it from the ground, and it goes up, 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 till it reaches its apex, and then it comes back down and ends with a displacement, total distance covered, of 0 in the vertical direction. And this general equation is just a quadratic equation, y is equal to ax squared. So, quick rundown, horizontal is a linear, vertical is parabolic. Third big idea, draw the horizontal and vertical vectors. This was probably the hardest part of this unit, although it's still not very hard. So if we were to draw the velocity and acceleration vectors along an object's trajectory in both the horizontal and vertical directions, we would notice three things. The horizontal velocity vector does not change. There is no horizontal acceleration vector. And at the apex of trajectory, the vertical velocity vector is equal to 0. So here we're going to look at a little simulation that just runs through it pretty quickly on a physics classroom. That'll just give you a moving example of that photo right there. Alright, sorry it's a little bit off center, but here's our little physics class simulation looking at like drawing the velocity vectors and some of the things we noticed in the vertical and horizontal velocity vectors. So we have the ball, which I set at just 60 meters per second speed. It doesn't particularly matter, a 50-degree angle, and we're projecting it from a height of 0 meters. So first I'm gonna press start, and the ball is gonna go through projectile motion, and keep an eye on y displacement. You're gonna notice it's gonna go up and then back down. So the y displacement will be 0, but the horizontal displacement will be an unknown number. So let's press start, run through it pretty quick. Okay, so we see here that the y displacement was 0 and the x displacement was 361.7. Alright, so we're going to press reset and a time of 9.3 seconds. So now we want to look at how we're going to draw velocity vectors in the horizontal and vertical directions. So we're going to press show velocity vectors, and as you can see it already started out with some, and we're going to press start and see what happens. Okay, so notice there the horizontal velocity vector does not change, but the vertical velocity vector reaches its apex going up. Once it reaches here, it starts going down till it's at its maximum at touching the ground. Okay, and finally I'm going to click show acceleration vector, unclick show velocity, reset. Now we're going to look at the acceleration vector in the horizontal and vertical directions. And projectile motion, I'll press start. Okay, pretty quickly you can notice that the acceleration is a constant. Free fall, or acceleration of free fall on Earth, 9.8 meters per second squared, and there's no horizontal acceleration vector because there's no acceleration in the horizontal directions. My HDMI cable stopped working, so here we're just going to look at two problems, a medium problem and then a spicier IB problem, and review how to go through them using the SUVAT equations. Okay, so I ran through a medium and a spicy problem, so I'm going to work through them now quickly with you guys. Okay, so the first problem says it's just a steel ball projected horizontally and there's flash photos taken at 10.1 second intervals. So here is the graph. And these little black dots in the graph are the photos of the ball. So the first question here asks the constant horizontal speed of the ball. Well, that's a pretty simple equation. Distance is equal to velocity times time. So we know after I just chose the second dot interval up here, after 0.2 seconds, the displacement in the horizontal direction, if we're doing the constant horizontal speed of the ball, the displacement here is, it's hard to see on this, 0.36 centimeters. Okay, or 36 centimeters, sorry, 0.36 meters. So after 20 seconds, the ball has traveled, or after 0.2 seconds, sorry, the ball has traveled 36 centimeters. D is equal to VT, D is equal to VT, and 36 centimeters is equal to V times 0.2 centimeters, or 0.2 seconds. V is equal to 180 centimeters per second, or 1.8 meters per second. So that's the horizontal speed. And then part 2 asks the acceleration of free fall. So I chose 0.4 seconds because that's going to give us the longest time for the ball to speed up, and we can look at acceleration easier. So we were given displacement of 0.8 meters. It goes down, 80 centimeters in the horizontal, and a initial velocity in the vertical of 0 meters per second. Just starts out up here. A velocity that's unknown, in the vertical direction, unknown velocity, an unknown acceleration in the vertical direction, and a time of 0.4 seconds. So the best Suvat equation, which Mr. Hartman wrote for me here, is S is equal to ut plus 1/2 at squared, and that's the general equation we use to find acceleration in free fall. So we just plug our variables into that equation, and we get S 0.8 meters is equal to 0, which is u, the initial velocity, times 0.4 seconds plus 1/2 acceleration, the variable we're looking for, times 0.4 seconds squared. Well, 0 times 0.4 is 0, so we can just negate that, and we get 1.6, because that's 8.8 divided by half is equal to a times 0.16. Well, 1.6 divided by 0.16 is 10, so acceleration, free fall, is 10 meters per second squared, and that's pretty close to 9.8 meters per second squared, so we know we got that one right. Okay, the orientation last time was a little bit hard to see, so I switched it up a little bit. Maybe this is a little bit easier. Still, it's a bit hard to read, but it's my limitations of my camera. Okay, so this is our spicy problem. So, actually on the front here. Okay. So we have negligible air resistance, and we have three goals. We have to find the horizontal velocity component, Vx, 1 second after the apex, and the vertical velocity component, Vy, 1 second after the apex. I'll see if I can zoom in. Okay, so our second goal is to find the distance covered displacement here. Is Sx in the horizontal direction, and our total time in the air. So we are given the initial velocity of this stone that's being thrown is 40 meters per second in the horizontal and 30 meters per second in the vertical. And I did a little bit of a sketch here. See if we can zoom in. We start at 0. Here's our little vectors, 40 to the right, 30 up. Our apex with only the velocity vector in the horizontal direction, and our 1 second after the apex. Drawing our S of x, and downwards is positive, upwards is negative. Okay, so the first one, we want to solve the horizontal velocity component. That's our first goal, find the horizontal velocity component and the vertical. So with negligible air resistance, there is no acceleration in the horizontal direction. Therefore, Vx, 1 second after apex, is still equals 40 meters per second. That was fairly simple. The vertical velocity component takes some small calculations. So we know that the vertical velocity at the apex is 0 meters per second, and we also know that acceleration is equal to velocity over time, a is equal to v over t. So that's pretty easy. If the acceleration of free fall is 9.8 meters per second squared, is equal to v, y in the vertical direction over 1 second, 9.8 meters per second is equal to the vertical velocity 1 second after the apex. This makes sense, just gravity acting on the thing, on the rock. Okay. We have to skip over the second goal because we have to solve the third goal to go back to solving displacement. So for our total time, well, it's easiest to find total time by splitting a parabolic motion into two parts, the ground to the apex and the apex to the ground. This is something we should remember for our physics test. This is because finding time in parabolic motion deals with the y vector components, and we know the uy, the initial vertical velocity, and the vy, final velocity at the apex, is 0 meters per second. So here we are given our initial vertical velocity of 30 meters per second. We know the final at the apex is 0. We know the acceleration of gravity is negative 9.8 meters per second squared, and we don't know the displacement in the vertical direction. We don't know the time. So what Suvat equation do we use? Well, if we don't know the displacement and we want to find the time, we're going to look at v is equal to u plus at. So just plug our given information in. 0 is equal to 30 meters per second plus negative 9.8 times t. Negative 30 is equal to negative 9.8 meters per second times t. So negative 30 divided by negative 9.8 gives us 3.065 seconds as t. But we split the apex in two, and in parabolic motion there is no horizontal acceleration or deceleration, so the second half of the parabola is exactly the same as the first, Therefore, we can just double this number, and we get 6.13 seconds is equal to the time. Coming down to solve our third goal, or our second goal, displacement in the horizontal direction. So to solve displacement in the horizontal direction, we use horizontal vector components. We are given the initial velocity in the x direction as 40. The final velocity is 40, it doesn't change. The acceleration is 0. The time is 6.12 seconds, and we don't know displacement. So what's that equation? Well, here we can either use s is equal to u plus v over 2 times t, or s is equal to ut plus 1/2 at squared. I just use s is equal to u plus v over 2 times t because it's fairly easy and straightforward. S is equal to 40 plus 40 over 2 times 6.12. S is equal to 40 times 6.12. S is equal to 244.8 meters. That's our displacement in the horizontal direction. Our fourth big idea is projectile motion and air resistance. This is the final big idea. And this we did quickly in this unit, or at least in our packet. All we did for this was understand that an object's trajectory with air resistance has less horizontal displacement and less vertical displacement. There is actually, with air resistance, a horizontal force now acting on the object, and thus a horizontal acceleration. So that is it for this unit, and I hope this review was helpful.